Wonderful. Newton's method is one of the harder things in calculus for me because I don't get it very often. I would say about 10% of my high school calculus students have to cover Newton's method, but most of them don't. So you taking your college calculus class, I'm not terribly surprised that they're covering Newton's method. So I will do my best to explain it to you.
Okay.
Okay. First of all, back in the 1700s, actually the 1600s, when Newton lived, they were familiar with functions, and they knew what a function looked like. And for me to explain this, let's take this function x squared minus 2. Okay? I think we're both familiar with that. That's a parabola that's been vertically shifted down by 2 points, correct?
Mm-hmm.
Now, Newton looked at this and he said, how would I find the zeros? He didn't have a calculator, nor did he have any method of finding the zeros other than to say, well, 0 equals x squared minus 2, therefore x equals plus or minus the square root of 2. But he didn't have a calculator, so he didn't know what number plus or minus the square root of 2 was. And he wanted to know the number as exact as he could get it. So he came up with this method for approximating the zeros, which is amazingly accurate. And what it does is it requires you to start by guessing. Well, if I look at this function, even if I know that that's the square root of 2, let's make our guess 1. X sub 1 equals 1. That's what we're going to guess. Even though we can plainly see that it's greater than 1, I'm going to show you the power of Newton's method. Even when we make a guess that's really off, Newton's method is going to get to the correct answer really quickly. Okay? Now, here is the formula for Newton's method. At the top, and I know that's terribly complicated looking, but here's what it means. It means if you take your first guess, that's x sub 1, and you subtract from it the function evaluated at x sub 1, and you divide that by the derivative of the function evaluated at x sub 1, this whole thing produces an x sub 2 that is more accurate than x sub 1 was.
Wow, okay.
Let's do it for this problem. We know the answers, but let's pretend like we don't. Let me make some room here. And first of all, we're going to guess from our graph. We're going to make a very rough guess that x sub 1 is 1. In other words, we're going to assume the 0 crosses right there, even though we can plainly see that it doesn't. Anything close is good. If you get anywhere close on your first guess, then you're going to have almost a precise answer by your third iteration. And this is an iterative process. Every iteration produces a guess that is more accurate. All right, let's go through it. So if x sub 1 equals 1, then x sub n plus 1 means that's x sub 2. And that's going to equal x sub 1 minus f of x sub 1 divided by f prime of x sub 1. You with me so far?
Mm-hmm.
Okay. Let me erase that because this is really what we're looking at. So my second guess, x sub 2, is going to be equal, well, what's x sub 1?
Is it 1, right?
1, right there. It was a guess that I made by just looking at the graph. I guessed that the 0 might be at 1. Okay?
Mm-hmm.
That's our first guess, 1. Minus. What is the function evaluated at x sub 1? In other words, what is that? Remember, this is our function over here on the left. Evaluate it at 1.
So it's -1?
Correct? That goes in parentheses. That's the numerator of that fraction. Now take its first derivative, which means we need f prime. What's f prime of x equal to?
2x.
Now evaluate that. F prime at 1. What do you get?
2.
Okay, so that goes down there. And this tells us that x sub 2 is equal to 1 minus a -1/2, which is the same as 1 plus 1/2, 3/2. That's our x sub 2.
Okay.
You can see, especially knowing that the square root of 2 equals 1.41, that 3/2 is much closer than 1 was.
Mm-hmm.
Okay, so now we're going to figure out the third iteration. Remember, the third iteration is the second iteration minus f of x sub 2 divided by f prime of x sub 2. This will represent the third guess, and it'll be closer to the true answer than anything so far we have. So
Okay.
x sub 3 equals x sub 2, which is what?
3/2.
Minus, what is the function evaluated at 3/2?
Let's
In
see.
other words, what is f of 3/2?
It's 1/8 or 1/4.
I think. It's 9.
Yeah,
It's 9/4 minus 2, which is 1/4. Okay, so 1/4 goes in the numerator. Now take the derivative of the function, which was 2x, and evaluate that at 3/2. What is that?
3.
So here is our newest guess. It is not newest guess, I should say our newest approximation. Well, that is equal to 1.416667. Now we happen to know what the square root of 2 is because we have calculators and all. So we can figure out the square root of 2 to a lot of decimal places. And this is what it actually is out to 6 decimal places. That's what the square root of 2. In other words, that's our real answer. And notice how close we are with just the third iteration.
Yeah, wow.
Actually, only the second, because we guessed at 1 to start with, which was really a long way away. It wasn't even close to the answer. If we'd have guessed 1.4, we'd have really been a lot better off.
Mm-hmm.
Okay, now if you do one more iteration doing the exact same process that we've been doing, you end up getting 1.414216. Look how close that number is to the actual value.
Mm-hmm.
It's accurate to 5 decimal places. 5. That's astounding. And that's without knowing what the square root of 2 was, or without knowing that the square root of 2 was where the 0 was.
Mm-hmm.
Okay? So there is an illustration of the power of Newton's method. I mean, you can imagine back in the 1600s when they were trying to figure out zeros and they didn't have calculators or anything else, Newton's method was like a magic wand. With just a couple of iterations, you could calculate that 0 out to 6 decimal places. That's unbelievable. That's fantastic. So, let's do some problems that you sent. So, this function is 1/3 x cubed plus 1/2 x squared plus 11. That's the function. And we can set it equal to 0 since our problem is to figure out where the zeros are. That means f of x has to be 0, right?
Mm-hmm.
When you're on your zeros, your y coordinate is always 0. So if I want to solve for my zeros, then I let this be the case. I let my function be equal to 0. But how the heck, if I'm in 1690, how do I solve that? You don't have very many ways, but you got Newton's method. Okay? We're going to give you a little bit of help here by telling you what a good first guess would be. Now, in our world, I could always graph that on a calculator and get a good approximate first guess. Okay? And that's the kind of the way we work in 2017, is we use a calculator to give us an approximate first guess, and then we use Newton's method to refine it. Okay? Remember x sub n plus 1, and what that means is the next guess is equal to the first guess minus the original function evaluated at the first guess, all divided by the original function's derivative evaluated at the first guess. So at a very minimum, we need the first derivative. You always are going to need the first derivative if the problem is a Newton's method problem. Tell me what the first derivative is.
And we're taking it of the,
Of the original function, right.
Right, okay, so it's 3x squared.
Always start with the exponent. If I start with the exponent, I'm starting with the number 3. I'm going to multiply it by whatever the coefficient is.
Oh, right,
I'm going to subtract 1. So they made this problem like this so that the first derivative would be relatively easy. First term is x squared. Second term is x. Third term goes away. You with me?
Yes.
Okay, so let's figure out what x sub 2 is. So x sub 2 is going to be x sub 1 minus the function evaluated at x sub 1, all divided by the derivative of the function evaluated at x sub 1. In other words, all I'm doing is going from 1 to 2.
Okay.
Okay, now let's figure out what x sub 2 actually is. Well, what's x sub 1?
-3.
What's f of -3? In other words, yeah, here, let me blow this up a little bit so I got a little bit more good. What is, I need f of -3. That's what they're talking about right there. F of x sub 1, well, x sub 1 is -3, so they're asking me to evaluate the original function at my first guess. What is this become? What's f of -3? Let's just plug it in. 1/3 times -3 cubed. See what I'm doing? If you don't understand anything that I'm doing, be sure and stop me.
Okay.
So what I need to know is what f of -3 is.
Oh, okay. I was doing it in the... I was doing the derivative. Okay.
I plug in -3 wherever I see x in the original function.
Okay.
This is
Yeah.
minus 27 divided by 3 plus 9 divided by 2 plus 11. What that is minus 9 plus 4.5 plus 11. All of that comes to 6.5. That's what f of -3 is.
Okay.
Okay. So the numerator is 6.5.
Okay.
What is f prime of -3? Here's f prime.
6.
There's f prime. It's x squared plus x.
So it's 6.
So
it's -3 squared.
Yeah, I prefer that you always include this step.
Okay.
Because that makes it easy. In other words, I don't want you to do all that math in your head and come up with an answer. So all I want you to do is plug in -3 wherever you see x.
Okay.
Then simplify. Well, that becomes 9 minus 3 equals 6. So f prime of -3 equals 6. Now, you have a calculator in front of you?
Yeah.
What is the answer to this? What is x sub 2?
It is -1.58 and 333.
Do this on your calculator first. Come up with that number.
Okay. Oh, right. Okay. Okay, I'm gonna read that. That's what I did wrong. Sorry, one second. I'm just writing this down in my notes.
It's all right. That number is going to be a very small number. It's like 1 point something.
Yeah, it's 1.08333.
Now, when you do problems like this in your calculator, be careful. It's really, really easy to put them in wrong. You still have a TI-84?
Yes.
It's really easy to put them in wrong. So I kind of suggest to most of my students that they do it in parts. In other words, do the tough part first. The tough part is 6.5 divided by 6. Let's come up with that number and then subtract that number from -3. Well, that equals minus 4.08. That's x sub 2. Now, your problem wants x sub 3. Well, remember that x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. Well, we want x sub 3. That's going to be x sub 2 minus f of x sub 2 divided by f prime of x sub 2. Well, we just figured out what x sub 2 is. Let's plug that in. So now x sub 3 equals minus 4.08 minus, well, now we have to evaluate our function at minus 4.08. In other words, it's f of minus 4.08 divided by f prime evaluated at minus 4.08. That's a number. Now, there's still a lot of math to go. And I'm trying to figure out how much time we want to spend coming up with these oddball numbers. First of all, do you understand exactly what I'm going to do to come up with that number?
Yeah. We can just, I can do that
I'm going to go
on my
with
own.
my original function. I'm going to substitute minus 4.08 for x, come up with what f of minus 4.08 is.
Right.
I'm going to go into my original derivative, which I believe was x squared minus x. And I'm going to substitute minus 4.08 and come up with a number there. Then I'm going to have a number in my numerator, I'm going to have a number in my denominator, and I can come up with x sub 3.
Right. Okay.
And that would be a very, as we've already discovered, 3 iterations doesn't sound like much, but it gets you very, very accurate to the zeros. And I'll bet you this 0 is accurate to within 4 decimal places at least. So, rather, in other words, we've already spent a half an hour and we're still on the first problem, but part of that is I went through an example problem because I kind of felt that example problem explained it better.
Yes, it helped a lot.
Okay. So at this point, rather than coming up with this number, I can let you do that on your own. Let's go to the next problem and get it set up right. Is that fine with you, or do you?
Oh yeah, no, that's perfect. I'd rather get through the material than.
All right. Well, we're still not going to get through it all, but we're going to get through a lot more of it than if we came up with an answer for everything. So in this one, number 2, they give us the function, and they tell us the first approximation. If they didn't tell us the first approximation, the best way for us to get it is to guess or to graph it and guess based on the graph. They're making it kind of easy by telling us their first guess. Okay? So, tell me, hold on, I'm going to erase some of this other stuff. Give me the general formula for x sub 2. Well, first of all, before we go any further, we know for sure we're going to need the first derivative, right? Well, let's figure out what the first derivative is.
Okay.
What is it?
It's 5x to the fourth minus 1.
All right. Now, those are going to be part of every guess, f of x and f prime of x. Okay? General formula, x sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. I'm repeating this over and over because I can't imagine that I can repeat it too much. Okay? It's really worth memorizing this. So I've been given an x sub 1, so my first thing is to find x sub 2.
Right.
Well, tell me what x sub 2 is going to be. Well, let me write out most of it. It's the previous term. That's what, in other words, this says x sub n plus 1, this says x sub n. So in my case, I'm looking for x sub 2, so the first term has to be 1 less than that. Minus the function evaluated at x sub 1 divided by the derivative of the function evaluated at x sub 1. So there's a lot of preliminary steps here, but I think each one of them is worth taking. Now, tell me what x sub 2 is. What is x sub 1?
1.
Okay. What is f of x sub 1?
So it's 1 to the fifth minus 1 minus 3.
Which is?
Is negative 1. Or wait, no, that's in minus, sorry. 1.
Okay, so here, we're going to do f of 1. Let's plug it in. It's 1 minus 1 minus 3. That's equal to minus 3. And while we're at it, let's figure out what f prime of 1 is. What's f prime of 1 equal to?
4.
Okay. So now I got 1 minus f of 1. Well, f of 1 was minus 3. Put it in parentheses. It's real easy to drop negative signs in these problems. And f prime of 1 was 4. So if you do the math, that's 1 plus 3/4. Let's call it 7/4. I like my answers in improper fractions better than proper fractions. Okay?
Okay.
So now we have an x sub 2. That's a lot different than x sub 1. So we can assume that this is a lot closer to the real solution than our first guess, which was 1. Okay? So they want an x sub 3. So x sub 3, tell me what x sub 3 is going to be generally.
So it's going to be...
Start with
7.
x sub 2.
Alright, so x sub 2 minus f of x sub 2 divided by f prime of x sub 2.
Now we can go specifically. So what's x sub 2?
7/4 minus...
What is f of 7/4? In other words, what is f of 7/4?
Let's see, it's 7/4.
We're going to need f of 7/4 and we're going to need f prime of 7/4 to get to our answer.
Right.
So, wow, why would they make this so hard?
I can go back and do this. I think I got...
All right, it's 7 to the 5th over 4 to the 5th minus 7/4 minus 3. That's what f of 7/4 is. You see how I got that?
Yeah.
Okay. F prime of 7/4 is 5 times 7/4 to the 4th minus 1. So my final answer, I hate it when they make these harder than they necessarily have to be. That's the numerator. The denominator by making these overly difficult, they just make them more confusing. I mean, why couldn't they use whole numbers to illustrate principles? What I've circled is the answer.
Okay. Right.
Now, it would take me 10 minutes to come up with what that number is. It would, even in a calculator. Because I'd be afraid of putting it in wrong, especially with a TI-84. You almost have to figure out what 7/4 to the 5th power is, substitute that, figure out what 7/4 to the 4th power is, substitute that, multiply that by 5, come up with a numerator, come up with a denominator, figure out what that number is. In other words, you almost have to do it in like 4 steps, even if I have a good calculator.
Yeah.
Only because they made it so difficult.
I know, always.
You can imagine that if I had to come up with x sub 4, how much more difficult it becomes. Because these fractions, I mean, I went from 1, my first guess, to 7/4, my second iteration, to this number, which God knows what that number is. But it's certainly complicated. It's not a nice round number. And then we'd have to deal with that number as our third guess. And of course, our fourth guess would be that number all over again.
Right.
And thank goodness that Newton's method is so good that you rarely have to do more than 3 iterations. Or you come up with an answer that's very close to the exact number that we now can figure out because we have computers and calculators and graphing calculators. So all you have to do to figure out the zeros of this function is plug it into your graphing calculator, put it on trace, and find the zeros.
Yeah.
So one reason that there's not a lot of teaching anymore of Newton's method is that, 20 years ago it would have been different. 20 years ago they were using Newton's method. When I went to college, they were using Newton's method. But once they came up with calculators that could figure out the zeros, well, now it's not so needed. But it is still a wonderful development of math. In other words, where in the world did they come up with this? I could go through the math on how they got that, and it's interesting, but it's pretty complex, and I'm not sure it's worthwhile. The only thing you have to know is that function, what I've circled in the upper right. Definitely have to memorize that. And you have to understand what it means. In other words, if this is one guess, then we're looking for the next guess. And no matter what n is, you can just keep getting more and more accurate by more and more guesses. In other words, x sub 9 would be maybe accurate to 15 decimal points. Who knows? All right. Let's go on to number 3. Are any of these different? Yeah, this only asks for x sub 2. Why do they only ask for x sub 2? It's interesting. They don't usually get easier, do they?
No.
So first of all, let me get this so where I can write it on my paper and then we can go through it and figure out why this is problem number 3, because that's abnormal. So here's my function. And I really don't have any idea what the zeros are of that function. But again, they're going to give us their first guess. X sub 1 equals 1. And the only thing they want is x sub 2. I bet I know why this is number 3. First of all, there are some functions where Newton's method does not work. Let's talk about that, because that's worth knowing. I think you understand what's going on here. If I had the following function, it doesn't work. In other words, my first guess, if I'm looking for the zeros of that, let's say my first guess was 1. Well, this is all based on the slope of the tangent line. It means my next guess is there. Now I take the slope of that tangent line, and notice that each guess is getting me further and further away from my 0.
Oh, yeah.
Each guess gets further. The true 0 is at 0, but because of the nature of this function, particularly because of the fact that it's not differentiable at our true 0, notice that it has a vertical slope of the tangent line. So if it is differentiable, but the derivative is infinity or undefined at our actual 0. And if you took this function and tried to apply Newton's method, it would not work. You would keep getting further and further away from the real 0. So a good thing to know about Newton's method. Certain shapes of functions, it doesn't work very well.
Okay.
Well, I'm kind of guessing that this might be the case here. I don't know for sure, but I'm going to guess that it's the case merely because what is this doing is problem number 3. And the first two problems wanted x sub 3, and this problem only wants x sub 2. Well, what's the first thing I know I have to do? Always, with Newton's.
Take the first derivative.
Which is?
4x to the third minus 1.
Okay. Now, x sub 2 equals, give it to me in terms of x sub 1.
So.
In other words, I'm not going to make you repeat the general formula, but give me the specific formula for this without numbers, just in terms of function notation.
F of 1.
Well, let's call it f of x sub 1.
X sub 1, yeah.
Let's do it that way. I think this is an important step. Okay? In other words, starting out there.
Okay, so it's 1.
The true place to start out is up here. X sub n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. That's the true starting spot. But since we're trying to figure out x sub 2 specifically, the next step would be that. Okay, now let's plug in everything we know. What is x sub 2? What's x sub 1?
1.
Minus f of 1 divided by f prime of 1. So let's go up here. Hold on, let me erase this so I have room. What is f of 1 equal to?
Oh, it's 1 to the 4th minus 1 minus 3, so negative 3.
What's f prime of 1?
Is 1.
Plug it into this one down here.
Oh,
It's where I'm pointing.
oh, sorry, I don't know why.
I was trying to point with my cursor, and I don't think you can see it. Can you see this where I'm pointing right now?
No.
Okay, can you see it now where I'm pointing?
Yeah.
Okay, one is with my mouse, the other is with my cursor. I wasn't positive, but I figured that that's the way it worked. So evaluate that at 1. What do you get?
Oh, it's 3.
Okay. Now let's figure this out. So plug in the numbers. 1 minus what?
Negative 3 over 3, so it's 4/3.
Hold on. What's negative 3 over?
Oh, wait, I keep doing that. I don't know why I keep putting the whole thing over.
It's all right.
Okay.
The arithmetic,
Oh, so that's negative 1.
The arithmetic part is easy. If you can if you can understand the calculus part, you're fine, even if you get the arithmetic part wrong. Because if you put all these preceding steps, your teachers, well, maybe not on these computer online tests, but in general, if you were to lay it out all out exactly as I have done here, and then you got the wrong number, I'd give you 90% credit if I was the teacher. I wouldn't certainly take off 100%. You've done everything right. The only thing was maybe the arithmetic. Well, what does that equal to?
2.
All right. That's x sub 2. Okay. Now, the question is, what is this problem doing where it's at?
Here I can, let me pull it up really fast.
Why don't you try putting that answer in and let's see what it tells you. Can you do that without doing 1 and 2?
Yeah.
Okay.
It'll take me 1 second.
Put in 2 for that. Well, let's see what it tells you.
Yep, that's correct.
Really?
Mm-hmm. Interesting.
Now my curiosity is getting the better of me, and I want to put this into Wolfram Alpha just to see where this 0 is and why do I not have Wolfram Alpha on my lists here? Oh, here it is. So this function, in other words, Wolfram Alpha will tell us where the zeros are.
Mm-hmm.
And I'm just curious as to why this problem wasn't first. Why is it third? The first 2 problems were much tougher.
I know. I don't.
Now notice where the zeros are.
Mm-hmm.
Minus 1 and change and about 1.5. Well, we just came up with 2. We're a long ways away from it.
Hmm.
In other words, the actual zeros, because Wolfram Alpha gives those to you, minus 1.1 and 1.45. We're nowhere near those. I guess the moral of the story is that all functions are not the same, and you're not going to get necessarily the same degree of accuracy using Newton's method as you might with another function.
Mm-hmm.
In other words, we didn't go out to the third derivative here, or the third approximation, although I kind of wish we would have, just to see that if we're getting closer to that real 0. But notice we're nowhere close to the negative 0. There were 2 zeros here. You still there, Mark?
Yeah.
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 And we're nowhere close to it. So the reason this may be question number 3 is to illustrate to you that this doesn't always work that great.
Oh, okay.
So I would have thought that they'd have proved it more by making us find x sub 3. Not only that, x sub 3 would have been pretty easy to find on this function because x sub 2 came out to be a whole number.
Yeah, really.
The previous 2 problems, x sub 2 came out to be a fraction, which made finding x sub 3 all the tougher. So when x sub 2 comes out to be a whole number, gosh, x sub 3 would be a piece of cake. Not that I necessarily want to do it. Let's not. Let's look at the next problem just to see where they're going with this, because it's a little hard for me to understand their order of problems here. All right. They give you an example here. And this is a great example because the equation they're trying to solve is cosine of x equals x. Well, without a calculator, I got no chance of solving this. With a calculator, yeah. Notice what they graph. They graph the cosine of x with one function, and they graph y equal x with another. So all you got to figure out is where they cross. That's the answer to the equation. It's a little less than 1. Okay? So it's a little number less than 1. So we first rewrite the equation in standard form being where you end up with 0 on one side, everything else on the other. And now we let f of x be that function. Yeah, I'm pointing with my mouse. So what's f prime of x equal to?
So it's 1, or so the derivative of cosine is, it's 1 over the root of.
No, the derivative of cosine is negative sine.
Oh, just, right.
What's the derivative of minus x?
1, or negative 1.
Minus 1. Notice that's what's in this denominator over here. The derivatives.
Oh, yeah.
Okay? And look at this function they're telling us. X sub whatever sub we want is equal to the first approximation minus the function evaluated at the first approximation divided by the derivative, which is this. So we end up with this over here. Now, in order to guess a suitable value for x sub 1, we sketch it. What would be a good guess for x sub 1? Looking at the graph.
A little less than 1.
Let's guess 1. Sure.
Okay.
In other words, yeah, I could guess 0.9, but let's not make things difficult. Let's guess 1. Okay? And it appears that they intersect at a point slightly less than 1, so let's take x sub 1 as 1 as a convenient first approximation. Then remembering to put our calculator in radian mode.
Okay.
That's key. Anytime you're doing calculus, you want to be in radian mode. Calculus does not work in degree mode. If I said, what is the first derivative of the sine of 90 degrees, it is not the cosine of 90 degrees. Gotta be in, and I can't really explain to you why, just trust me.
Okay.
It's really a difficult, I'm not sure I could explain it. It all has to do with the basic difference between degrees and radians.
Okay.
I've probably said before, but degrees and radians are not related in the same way that feet and inches are. or for that matter, feet and meters. Feet and meters are the same linear measurement. They're just one's in Europe and one's in America. Okay, and there is a exact relationship. There is 39 inches in a meter. So they're the same thing, just different units. Well, I can't say the same for radians and degrees. And the best I can tell you is that degrees are 1/360th of a circle. Radians are numbers. Radians are numbers. They're not degrees. They are numbers. That's why radians are what's needed in calculus, is because radians are numbers. When you take the cosine of something, you don't want to take the cosine of degrees. You want to take the cosine of a number, a radian. And that's the best I can do to explain it. Okay? Now, if you use x sub 1 equals 1, and using this formula up here, you get an x sub 2 of this, an x sub 3 of that, an x sub 4 of that, and x sub 5 of that. Notice how close x sub 4 and x sub 5 are. Do we need to do an x sub 6?
No.
In other words, the way you figure out that you are close to your final correct answer is how close your iterations are to one another. Notice that when we went from x sub 2 to x sub 3, it changed by 11 thousandths. Okay? But then when we went from x sub 3 to x sub 4, it changed, but not by much. But it still changed. Those last 4 digits are considerably different than those 4 digits.
Right.
But then when we went to x sub 5, it didn't change at all. X sub 5 is accurate to 7 decimal places to x sub 4. That means our true solution, if I were to put this into Wolfram alpha, let me do it real quick, I've got it. Cosine x equals x. Cosine x equals x. Let's see what the absolute number is. 0.739085. 0.73908513. That means our fourth approximation was more accurate than what Wolfram alpha gave me. So Newton's method is powerful. Even on complicated problems like this, which, God, in Newton's day, that would have been a bear to do. Without a calculator, how would you do that? Really hard. But Newton's method got the answer to 5 decimal places in just the 4th iteration. But this is an excellent illustration of when you stop. Since x sub 4 and x sub 5 agree to 6 decimal places, and in reality it's 8, you count them, 1, 2, 3, 4, 5, 6, 7, 8, we conclude that the root of the equation is, and they only need it to 6 decimal places, so it would be 0.739085. If you want to enter that as an answer, that's correct.
Yes, I did.
I don't know if you can enter them out of order or not.
Yeah, I did. It's correct.
Okay. All right. Let's stop there.
Okay.
What was that? That was problem number 4. I love the way they do this, actually. Well, other than the fact that problem number 3 should have been problem number 1.
Yeah.
But I like them sticking this number 4 in, which is an example problem that they give you a lot of the answers. It's terrific.
Yeah.
It really enhances your understanding of the problem, this example problem. And then they're going to give us one that they're going to expect us to use. Actually, number 5 doesn't look any tougher than 1, 2, or 3. You might even be able to do it without any help.
Okay, yeah, and I think the other ones have video examples, so that I think I get stuck.
By all means, you can watch the video of this, which I should have up there by tonight, maybe not, if not tonight, tomorrow morning. And it'll show you exactly how to do them, and I'll bet you can do number 5 on your own.
Okay, sounds good.
Yeah.
Yeah, I definitely have a good understanding now, so.
Good. All right, Morgan, have a good night. I'll talk to you next time.
All right, you too. Bye-bye.
Bye-bye.